And now for the exciting finish of inverse trig notes. We got pretty far yesterday when we were talking about inverse trig. We finished up with sine, cosine, and tangent inverse all in our back pocket. We learned in which quadrants these things can return values to us, right? Sine inverse can only return values from quadrants -1 and +1. Same thing for tangent inverse. Only difference is tangent inverse doesn't include -π/2 or +π/2. And cosine inverse can only return values in quadrant 1 or 2. That's what we were working on yesterday. So we haven't learned about graphing yet. So if you were going to have to do a question like this on a test, I would give you a picture of it. It says, describe the end behavior of tangent inverse of x. Well, here's what we're going to do. We're going to come right here to see this picture for tangent inverse x, and I'm just going to draw it over there, and then we'll write in the end behavior using limit notation. Cool with that? Yes? Okay. Alrighty, looks like it goes through 0 and is shaped like a cube root function, but it is approaching +π/2, -π/2. Cool. All right, let's get that handled. So the question might be, why is tangent inverse undefined at π/2 and -π/2? Well, the reason why is because at π/2 and -π/2, our coordinates on our quadrantals would be 0, 1 or 0, -1. Either way, they both have an x value that is 0, and tangent of theta is y/x. So since tangent is undefined at π/2, tangent inverse does not have π/2 in its range. Because π/2 is not in tangent's domain, it is not in tangent inverse range. Our graph looks like this. Forever approaching those asymptotes, but never actually getting to them. So we're just going to describe that behavior. On the left, the limit as x approaches, well, let's see, x values that are way far out to the left would be -∞ of our function, which is tangent inverse of x. Where are the y values headed as my x's go left? Down to where? -π/2. That is a horizontal asymptote that we will never reach, and that's because tangent is undefined. You cannot do tangent of π/2, so π/2 does not exist, and -π/2 does not exist in tangent inverse's range. Now the limit as x heads to the right, +∞, my graph is technically increasing forever, but it's heading towards the value π/2. That's it. This was really just a recap of, do you have the ability to use limit notation to describe our endings? That was really it for that one. So back to actually using some trig inverse. So there it is. In this question, what we'll be doing is composing inverse trigonometry with standard trigonometry. We've been asked to compose each of the 6 basic trig functions with sine inverse of x. That means I need to find sine of sine inverse, cosine of sine inverse, tangent of sine inverse, and all 3 reciprocals of sine inverse of x. We're going to reduce this new function, this composite function, to an algebraic expression that has no trigonometry in it. You'll see what's going to happen here in just a moment. First, we have sine inverse of x. Now, yesterday I told you, what is the result of every trig inverse? No, that's angle. The result of every trig inverse is some angle. Some angle. Now, we don't know much about this angle. For all we know, it could be ridiculously big, like 7 pi over 6 or something, puts us all the way over in quadrant 3. We don't know. But what we do know is that sine inverse can really only deal with things from a certain set of numbers. They can only return values to us in quadrants -1 and +1, which means that theta has to be acute. It's either positive acute or it's negative acute. It doesn't have a choice. It's one of the two. But to make life easy, what we'll do is we'll assume that it's acute. Okay? We'll assume acute and we'll assume positive. And the reason why we want to do that is because in quadrant 1, sine and sine inverse will cancel one another. So what I'm going to do here is I'm going to take the sine of both sides of this equation. Now, because sine is an operation, I can do it to both sides of the equation. Again, I said we assume that we're positive acute. That means assume quadrant 1, and in quadrant 1, sine and sine inverse literally cancel each other out, leaving us with the statement sine of theta equals x. Okay, the -1 is part of the structure. That's sine inverse. It's not an exponent. It is part of the function. Okay. So we have sine of theta equals x. But isn't it true that the result of every standard trigonometric statement is a fraction, a ratio of side lengths? I mean, it's sine. Sine is supposed to be y values over r values, right? Has to be a fraction. So what's its denominator? 1. Here's what this says. It says there is an angle that has the side opposite from it is an x, and the hypotenuse or radius is a 1. And we've already said that we're assuming we're in quadrant 1. So let's go ahead and draw that. Draw quadrant 1. Picture not on scale, obviously. And our theta is here. What we know about this theta is that sine of this theta, which would be opposite over hypotenuse, or the y value over the radius, is x over 1. That means the length across from our theta has a value of x. That is not to be confused with it being isosceles, oh, this is x and this is x, it must be 45. No, no, no. It means this is an unknown value, the unknown value x, not the coordinate x, okay? The radius or hypotenuse is a 1. How would I find the side that is adjacent to this theta? How do I find an unknown side? Yeah, it's Pythagorean theorem. We're just going to perform the Pythagorean theorem on this triangle with an unknown theta to figure out what A has to be. So good old Pythagorean theorem. A squared plus x squared equals 1 squared. Of course, 1 squared is 1, right? And we're trying to figure out what A is. So we're going to isolate A. Start by subtracting x squared from both sides. There is no reason to write 1 squared anymore. And then we take the square root of both sides. Now we have a value for A. Do I need the plus or minus? Somebody said no, why not? Yeah, because we're quadrant 1. It has to be positive. It doesn't have a choice. Oh, Mr. M, couldn't I just take the square root of this 1 and the square root of this x squared and say it's 1 minus x? No, absolutely not. Bad algebra. No. If it's 4x squared, you could take the square root. You can do that when there's multiplication or even division with a fraction bar, but not with addition and subtraction. Don't even try. You can't. This does factor 1 plus x, 1 minus x, but seeing as how those aren't the same things, you can't take the square root. No, that adjacent side has this value, square root of 1 minus x squared. Let's go ahead and redraw the triangle where I have more space. Only this time it won't say a, it'll say square root of 1 minus x squared. So again, I am in quadrant 1. I have some triangle. I have theta. I know it's a right angle. And my side lengths. Could we agree that theta is sine inverse of x? That this purple theta right here, if I had to write in a value for it, I could write it in as sine inverse of x, because, you know, sine inverse of x equals theta. Comfortable with that? I'm not going to write sine inverse of x, but I'm going to say sine inverse of x every time I do my trig, instead of saying theta. What am I talking about? Here's what I'm talking about. What haven't I used yet? Pink. Let's use pink. Sine, instead of saying of theta, I'm going to say of what theta equals. Is, so you see, instead of saying sine of theta, I said sine of what theta equals. Theta equals sine inverse of x. Yes, it's like a form of substitution. I'm in quadrant 1. So what do sine and sine inverse do here? Cancel each other out. Or if you weren't comfortable with that, you could just say sine does opposite over hypotenuse, x over 1. Either way, you were going to get x. And if we know sine, we also know cosecant. Cosecant of theta, but instead of theta, I'll say what theta equals. This one will be what? 1 over x. Someone in the back whispered it. You're about to find out why we needed to do all that. You're going to find out in a moment why we needed it. Just go. You're going to find out in a moment why you need it. It's super important to Calc 2. This is where you learn it, though. Let's do cosine of theta. But instead of theta, you know, what theta equals? Sine inverse of x. Cosine, good old SOHCAHTOA, is adjacent over hypotenuse. Looks to me like it's going to be the square root of 1 minus x squared. And if you know cosine, you know the reciprocal function, secant. And then the last two, tangent and cotangent. Tangent of theta, or what theta equals, is the y value over the x value, also known as opposite over hypotenuse. Or you could say sine theta over cosine theta. Either way, you're going to get x over the square root of 1 minus x squared. And then cotangent. Same fraction, just upside down. Okay, so, I'm sorry? Cannot, irrational? Yes. Imaginary? No. Well, not it at our level of mathematics, no. Could we draw triangles in the complex plane? Yes, we can. And then they would have technically, quote unquote, imaginary sine lengths. And we will do that in chapter 6. But for now, we're dealing with triangles in the real world. So what that does is clearly it puts restrictions on x, doesn't it? What it does is it tells you x must be between -1 and +1. Because if you go outside of the values -1 to +1, you would get an imaginary side length, which is not allowed. But why would you want to do it? Alex says. Okay, Alex, well, let's just say for the sake of argument, I tell you that sine inverse of x is 1/2. So then I say to you, what is the cosine of the sine inverse of 1/2? Cosine of sine inverse of 1/2 would be the square root of 1 minus 1/4. Well, 1 minus 1/4 is 3/4. Square root of that is √3/2. So what these do is they give us algebraic ways to evaluate trig inverse and standard trig together without having to draw all the triangles. It's also super important for something called integration by trig substitution in Calc 2. Unfortunately, it can't be seen on the video, but everybody in the room can see this board to my right with all this black writing. That's one question. That's one question, and you'll notice that triangle there with the theta in it as a hypotenuse of x, an adjacent side of 3, and an opposite side of square root of x squared minus 9. It uses this information to pull that off. One big, amazing question. So yes, it has use. We use it all the time in upper level mathematics. And yes, it's on your test. You'll be expected to compose your standard trig functions with sine inverse or cosine inverse or tangent inverse. So you need to be able to construct the triangle using the information that you're given. You need to be able to use the Pythagorean theorem to fill out said triangle. Make sure you have all three sides. And then just realize that this theta represents this trig inverse. So you're just evaluating sine, cosine, tangent at the trig inverse, the normal way you would. And you just compare the two sides. But it gives you an algebraic way of evaluating things without drawing any triangles. Yes? But it could, well, x is not allowed to be 0 because that would make these two undefined. But at 0, 2 of them happen to be undefined, yes. But not all of them. Like if for this one, x can't be 1 or -1, right? So they have limitations on them, just like tangent inverse does, you know, or tangent does, or cosecant. They have limitations. And this last question is holy smokes hard, so we're not even gonna bother. So we're just gonna skip that. All right. So Guten Tag again. For the rest of the period, we're just gonna do some practice questions. What do you think? Just some practice inverse trig stuff? All right. You are welcome to write on the whiteboard tables if you'd like to, but you might want these for notes. But if you're going to write on the boards, then just help yourself to an eraser in that cabinet. Your first practice question goes like this: cosine inverse of -√3/2. We're going to evaluate cosine inverse of -√3/2 by hand, and I would like we will get the answer in radians. We'll get the answer in radians. I don't think I can say it enough times. The result of trig inverse is always an angle. So cosine inverse of -√3/2, you think of that as saying equals theta. That means there is an angle for which cosine is equal to -√3/2. But here's the kicker. Cosine is negative in 2 quadrants. But only one of those 2 quadrants is allowed to be part of the range of cosine inverse. Where's the first time cosine would have been negative? Quadrant 2. So that is the quadrant that cosine inverse has in its range, quadrant 2. Quadrant 3 is not in any of the 3 basic inverse trig functions range. And I said that because cosine is also negative in quadrant 3. Because it just needs negative x values. Picture not on a scale. remember, theta is outside of the triangle. We'll be working with some reference angle that I'll put a green dot for. We'll be referencing the green dot, but this is our actual answer. So what do we know? We know that the x value is negative root 3 because the radius cannot be negative. In this triangle, which is a special right triangle, what is the unknown side right now? What is this value? It's a 1. So this is a 30, 60, 90 triangle. In degrees, since this is a 30, 60, 90, what is the size of my green angle? This is a 30-degree angle. But a 30-degree angle is what size in radians? 1/6 of a pi or a pi over 6. So if this is pi, because it is quadrant 2, and the size of this angle is a pi over 6, what is the size of theta? It's the other 5 pi over 6. That's the answer. So bonus question. And I'll tell you, no more work needs to be done to see this answer. It's on this paper already. It's not 5 pi over 6, clearly, because the result of standard trig is side lengths. Remember, cosine inverse of negative root 3 over 2 is theta. So this question actually says sine of your theta, which is 5 pi over 6. The question actually says, what is sine of 5 pi over 6? It's 1/2. Y over R. Bonus question. You know what? I'll hold on to that one for a minute. Let me just hold on to it. Let's do one on the calculator. Let's do a calculator question. First of all, we're going to get our answer in radians, not degrees, because I'd rather use radians. This is not a special right triangle in any way, shape, or form. You don't need to worry about that. In which two quadrants is tangent negative? Two and four. Tangent is negative when x and y don't have the same sign. So tangent is negative in quadrant 2, where x is negative but y is positive, and tangent is negative in quadrant 4, where x is positive but y is negative. So my triangle is either here or it's here. That's what I know. It's one of those two. And it's opposite over adjacent. So this side, or y over x, doesn't really matter. This side of this triangle would be negative 0.1234, and if the adjacent side must be a 1. Excuse me, I'm talking ridiculousness. There we go. Because 0.1234 divided by negative 1 is negative 0.1234. Or it could have been in quadrant 4, where the x is positive and the y is negative. Either way, tangent of theta will be negative 0.1234, right? But in order to get theta by itself, I'm going to have to utilize tangent inverse. To cancel this tangent, I need to use tangent inverse. So we do tangent inverse of both sides, which is an operation that can be performed on opposite sides of an equation, leaving us theta equals, and then we go to town. We know that theta equals the tangent inverse of negative 0.1234, and grab my calculator. I said we're going to do it in radians. Make sure your calculator is in radian mode. Mine is not. My calculator is currently in degree mode. Press DRG, scroll over radians. There we go. Now we're in the rad mode. Tangent inverse is the white command above tangent. So I do second tangent, and then just negative 0.1234, close your parentheses. It told me that theta was negative 0.123-ish radians. So where did it put that theta? It put it in quadrant 4 / quadrant -1, because tangent inverse cannot exist. Its range does not exist over here. Tangent inverse's range is quadrant 1 and -1, from negative pi over 2 to positive pi over 2. That's what had to be there. Why? Because remember, trig inverse is trying to be lazy. Your job was to find a way to get all of the positive and negative values of tangent without repeating any values. And also trying to stay as close to 0 as possible. So I could go way over here for negative tangent values, but that's a big old obtuse angle when I could have just gone here and gotten the exact same tangent ratio. So going this way gives me acute answers. So it's less work, so to speak. The angle doesn't have to open as far. Okay? Okay. Cool. Alrighty. Earlier, someone was like, how would you have done that without a calculator? The answer is a tool, or is that yesterday that somebody asked that, or was that my first? Oh, and I said the slide rule? Yeah. You should have Googled it. Okay. Let's get another question. Let's get another question. No, the slide rule was made so that you didn't have to use a piece of paper that had it all printed on it. Stuff like that. You want to know how they calculated them in the first place? There's a lot of ways of calculating things, but more than likely they use something called successive approximations, which means guess halfway between where you know it, like you pick an upper and a lower bound. I know it's bigger than this number, I know it's smaller than this number. So you go, I'll go halfway between and see if I was right. If you were below the correct answer, then you go halfway between the 0.5 and the upper bound, and then you check again. And every time you figure out, was this above or below where I should have been, and then you cut the distance in half between. And it's just called successive approximations. The graphing calculator does things like that, but it also probably uses a lot of Taylor series, Maclaurin series, Fourier transformations, all kinds of very, very upper level mathematics type stuff. Oh, that's a sine. That doesn't make any sense. There you go. Sine inverse, sorry. Sine of -1/2 radians. Sorry. Now, sine inverse of -1/2. You should be able to get a theta from this. And I'll throw a bonus question on this one. This says there is a theta such that sine of that theta would be equal to -1/2. That's what this says. The problem is sine is equal to -1/2 in 2 quadrants. However, one of those 2 quadrants is not in the range of sine inverse. So our job is to ask ourselves, in which quadrant would we find sine hitting negative values first while staying close to 0? Quadrant -1, aka quadrant 4. So I'm not going to draw this in quadrant 3, which sine is also negative in quadrant 3 because negative y values. Now I'm going to draw it in quadrant -1, also known as quadrant 4. The reason why I call it quadrant -1 is because we say it goes from negative pi over 2 to 0. We draw that triangle in this quadrant. Picture never drawn to scale. Got a theta here, got that going on there. And theta is y over r. Since r can't be negative, the 1 must be negative. What then is the x side? Square root 3. Good. So what is sine inverse here? Well, how about first of all, in degrees, what is the size of this reference? It's a 30-degree angle. But because it's in quadrant -1, it's negative 30 degrees. So as radians, it would be negative pi over 6. Because it's a pi over 6 clockwise. 5 pi over 3 passes through 2 quadrants that sine inverse can't deal with. Trying to be lazy. Trying to get there as quickly as possible with doing as little work as possible. And literally because we can't repeat any values. Because if we repeat values, so like sine in quadrant 1 is equivalent to sine in quadrant 2, that means we've repeated our y values for sine. No big deal. But the moment you turn its graph on its side, it fails the vertical line test. So in order for sine inverse to be a function, we restrict the domain of our sine function, so that way when we turn it sideways, we pass the vertical line test. And all that will make more sense after we do graphing. But that's another reason why we restrict it the way we do. So bonus question is, where's my bonus question? Here it is. What is cosine inverse of the sine of negative pi over 6? And it is not just as easy as it's already on the page. You evaluate this stuff from the inside out. So like I said, from the inside out. The first thing that we're going to need to do is evaluate sine of negative pi over 6. We could do that by looking at the triangle that's currently on the page. What is sine at negative pi over 6? Sine is going to be negative 1/2 because, y over r. So what this actually says is, what is cosine inverse of negative 1/2? That's what it actually says. Because those two red squiggly things are equivalent to one another. Remember, the result of all inverse trig is an angle. So we're going to be hunting for a different angle. I don't want to say theta because I've already used theta. So how about I use phi instead of theta? Very common other Greek letter that is used for angles. And then we go, fine, there exists an angle phi such that cosine of this phi equals negative 1/2. The issue here is that cosine is negative in 2 quadrants. So trying to do as little work as possible, which of those 2 quadrants would keep us close to 0? Quadrant 2. So cosine inverse's range is from quadrant 1 to quadrant 2. This triangle, therefore, must be in quadrant 2. Phi is here, but the triangle that uses this orange dot as its reference has values of negative 1/2, x over r. Since r can't be negative and we know that x is negative over here, we draw it like that. And the question becomes, what side length is across from the orange dot? It's a square root 3. Therefore, the size in degrees of my reference angle is 60 degrees. And as radians, the 60 degrees would be pi over 3. So what is the size of phi if pi over 3 is here? 2 pi over 3. So as it turns out, the cosine inverse of the sine of negative pi over 6 equals 2 pi over 3. Radians, of course. Isn't that fun? Now, if I had just used a composition like we built in the notes, then I would not have required triangles. That's why we have these kinds of things. It gives us algebraic ways of solving that question without drawing all the triangles, which does have its merits in upper level mathematics. And I think we have time for one more. Wait, oh yeah, we have a question. What's up? So anytime you're answering a trig inverse question, an angle is your answer. So what we knew then is that this trig information here represented some angle. That's what we know. So we drew the triangle that creates this ratio and evaluated, the triangle that uses this angle, evaluated it so that we would have side lengths, because then it says trig inverse of side lengths returns back an angle. The result of all trig inverse is always an angle, always. So at the very, very end, it was going to be equal to some angle. We just have to go from the inside out. Would you like to do another one like that one where you have to work and move quadrants? Because I can make one up real fast. Yeah? Okay. And let's see, making this one up on the fly. Let's do tangent inverse of cosine of negative 1 over root 2. Wait. That's not possible. This is what happens when I make them up on the fly. Again, this was supposed to be an angle. I wrote side lengths. Try again. This is what I meant to do. I was thinking of what I wanted the answer to be. There. Give you some think time. Think time is up. First thing we want to do is figure out what the cosine of 3 pi over 4 is. Now, like I said, accidentally when I was writing the question, I wrote what I wanted the answer to be. If you draw 3 pi over 4, that puts you in quadrant 3. Two, I said 3, but I meant 2. Sorry, I drew it in the right place. I just said the wrong thing. This is then our angle. Of course, we'll be using this green reference angle. Well, if outside here is 3 pi over 4, then the green reference angle is a pi over 4, also known as a 45-degree angle. This is a 45, 45, 90. So 1, 1 root 2, except for the fact I'm in quadrant 2, which forces my x value to be negative. So cosine here is negative 1 over root 2. Like I said, I was writing what I wanted the answer to be. This question actually says, what is tangent inverse of negative 1 over root 2? And remember, the result of all trig inverse is an angle. I've already used theta, so I'll move over to phi. and then I will figure out the angle that is as close to 0 as possible, so I can do less work, for which tangent would have given me a negative ratio. Which quadrant would that have landed in? Quadrant -1, or quadrant 4, whatever you would like to call it. Because tangent is negative in quadrants 2 and 4, tangent inverse does not want to go all the way to quadrant 2. That's more work than it wants to do. It wants to stay close to 0, so we draw it here. So now I'm doing tangent inverse, so I'm trying to figure out which angle creates a triangle with these side lengths. Uh-oh. I should have done sine inverse. Okay, well, it's ugly. You're going to have to use your calculator to finish it. Unfortunate. Because it's not a special angle. I should have done sine. By hand? No, I should have used sine. The point is, just, here's what it says. Now, unfortunately, that's not a special right triangle. Well, I mean, it's this, but that doesn't do us any good at all, does it? Well, anyway, your answer, just so you know, would have been negative because it had to have opened this way. If I had done sine inverse, then this would have worked, but I got too excited. I wanted the answer to be -pi/4. And if it had said sine instead of tangent, this is what happens when you make them up on the fly. Whatever, the point is you could draw the triangle where it's supposed to be, and if this was the appropriate side lengths that I wanted, it would have made more sense. It's the dangers of making it up on the fly. Sine inverse would have worked perfectly. I should have used sine inverse. I was trying to be extra.